6.12.3 Isentropic compressor and pump efficiency. Compressors and pumps are devices for increasing the pressure of a fluid. Compressor is used to increase the pressure of a gas. Pump is used to increase the pressure of a liquid. Fluid enters the device at low pressure. Work is supplied to rotate the shaft in the compressors and pumps. As fluids pass through the device, the blades compress the fluid. So the fluid leaves the device at high pressure. So the compressors and pumps require work input. The energy balance in general form is shown here. We normally consider compressors and pumps are adiabatic. There is no heat transfer across the system boundary. And we also neglect the potential energy change and kinetic energy change across the system. So the equation is reduced as shown here. So this is the required work input for compressors and pumps. On a HS diagram, the location 1 is here. The state at the inlet is fixed. Let's say the pressure and temperature at the inlet is given. The outlet pressure is the desired pressure we want to achieve from the compressor. That is also fixed. Note that the state at the inlet and the outlet pressure are the same for both the actual process and ideal process. The ideal process will have the constant entropy at the given exit pressure. The ideal process will go through isentropic process, so it will have the constant entropy at the given exit pressure. So S1 equals S2S. So it goes straight up. So state 2S is here. S1 equals S2S. And the enthalpy at state 1 is H1. Enthalpy at state 2, H2S. So S2S minus S1 is the work input. This is the work input for the isentropic compressor. The exit pressure is given, which is the same as the pressure in the isentropic process. So this is the constant pressure line. But the entropy at the exit for the actual process will be greater due to the irreversibilities. So state 2 for the actual process will be somewhere here with a greater entropy. Entropy at this position is S2. And enthalpy at this position is H2. And the work input is H2 minus H1. So H2 minus H1 is the actual work input required for the compressor. So the actual compressor needs more work input to compress the fluid from pressure 1, P1 to P2. The isentropic efficiency of a compressor is the ratio of the isentropic work input to the actual work input. Note that the isentropic work input is in the numerator and the actual work input in the denominator. That is the opposite to the turbine. This is because for compressors, the isentropic work input is smaller than the actual work input. So we want to make the efficiency to be smaller than 100%. That is why the isentropic efficiency of a compressor is isentropic work input over the actual work input. Small number divided by bigger number. So the efficiency is smaller than 100%. Isentropic compressor efficiency can be also expressed in terms of enthalpy change. Example 6.14. For the compressor of the heat pump system, in example 6.8, determine the power in kilowatt and the isentropic efficiency using data from property tables. And we are going to skip part B. So in example 6.8, what is given as state 1? Pressure is 3.5 bar, temperature negative 5 degrees Celsius. State 2, pressure 14 bar, temperature 75 degrees Celsius. We want to determine the isentropic compressor efficiency, which can be expressed in terms of enthalpy change. H2S minus H1 divided by H2 minus H1. At the inlet and exit, we know the pressure and temperature, so we can fix the state. So we can determine H1 and H2. The only unknown is H2S. And we know that at state 2S, S1 equals S2S. And this is constant pressure line. So we also know pressure at state 2. So from the entropy and pressure, we can determine H2S. At the inlet, pressure 3.5 bar, temperature negative 5 degrees Celsius. Enthalpy, H1 is here, entropy, S1 is here. At the exit, pressure 14 bar, temperature 75 degrees Celsius, which fall between these two. So we can determine enthalpy at 75 degrees Celsius, average of these two numbers. So H2 to determine enthalpy at state 2S, we use S1 equals S2S. We also know the pressure at the exit. Pressure is 14 bar and entropy is 0.9572. So at 14 bar, the entropy 0.972, which fall between these two numbers, we can interpolate to determine enthalpy. So enthalpy So we have everything to determine the isentropic efficiency. So the isentropic compressor efficiency is 0.81. It means the actual compressor is 81% efficient relative to an isentropic compressor with the same condition.